In this video, we're going to be talking about the equilibrium of gases. So far, all the ones that we've talked about, everything has been in terms of molarity, and we've used Kc for that. So if you have gases, things tend to be in terms of pressures because we don't have molarities. So if you had a generic reaction, the same one we saw before, equilibrium, so A moles of A plus B moles of B forms G moles of G and H moles of H. What we end up with is essentially the same idea as Kc, but it's something called Kp. So this is an equilibrium constant in terms of pressure. And so again, it has no units explicitly, the Kp value won't, but we're assuming everything is in atmospheres. Okay? So it typically is exactly the exact same, it's literally the exact same thing. It is products over reactants raised to the coefficients. But now it's the pressure of compound G raised to the G times the pressure of compound H raised to the H, divided by the pressure of compound A raised to the A times the pressure of compound B raised to the B. Okay. So, yeah. It should feel fairly similar. If these were concentrations, this would be Kc. They're pressures, so it's Kp. So far, not a big deal. Let's look at an example of how Kp and Kc are related. So this example is going to be a little messy, and then we'll talk about it in general terms to kind of get it straight here. So we saw this on the last video. Saw this example. 2 NOs plus O2, the equilibrium forms 2 NO2s. Doesn't matter if this reaction is important or not, whatever. And we had a Kc value for this, 4.67 times 10 to the 13th. And we want to know, what is Kp? Okay. Well, essentially what we need to be able to do is relate molarities to pressures. So, some gas law stuff here. PV equals nRT. I do not need you to sit around doing gas law equations all day long again, okay? Well, pointing out a couple things here. N is moles, and V is volume, which is basically usually in liters. So if we can rearrange this equation to solve for N divided by V, that would be molarity. We want things to be in terms of pressure, so if we just divide V to the other side, we get nRT over V. N divided by V is molarity. Moles per liter, right? So basically it's just molarity times RT. So if we wanted to do this in terms of Kp, we could just do products of reactants. We're just going to set it up like that. So for this particular example, there's I'm already messing this up. It's the pressure of NO2 squared. Ignore that little thing there, sorry. Divided by the pressure of NO squared and the pressure of O2. Okay. Well, we said that P is essentially equal to molarity times RT, so for each of these we could plug in molarity times RT because that's what P is equal to. So this would be the concentration of NO2 times RT in the whole thing squared, because we're solving for the stuff in the parenthesis, or substituting in for the stuff in the parenthesis. Same thing down here. This would be concentration of NO times RT squared, and this is concentration of O2 times RT. So all these RTs makes things a little bit difficult. So if we were looking through this, this would be RT squared on top and RT cubed on the bottom. So basically the squared ones cancel out. So if you ignore the RT, this is basically NO2 squared divided by NO squared and O2, which is essentially Kc, and we have an RT on the bottom. So for this particular example, I will point this out because this is not always going to be the case. For this particular example, Kp happens to be equal to Kc divided by RT. I should point out here that R is, since this is everything is in terms of atmospheres, this is 0.0821 liter atmospheres per mole Kelvin, and T is just the temperature in Kelvin. Okay, so this is the messy way to get from here to here. But for this particular problem, this is how Kp and Kc were related. Okay, what we need is a more generalized form of this that works for any situation without having to go through all this stuff. Okay, there's nothing wrong with doing it this way, but I'm not going to ask you to do that. Okay. It turns out that in general, Kp is equal to Kc times RT raised to something that we're going to refer to as the delta N of gas. This looks like a much easier equation. So Kp we just defined, Kc we just defined. It's essentially, this is the equilibrium constant in terms of atmospheres. This is the equilibrium constant in terms of concentrations. R and T are constants. I'm going to rewrite them on here just so you have them. 821 liter atmospheres per mole Kelvin. And again, they're constants. I'll give them to you. And for this one, this needs to just be in Kelvin. Okay. This is the weird bit. This is the change in moles of gas from the reactant side to the product side. This is literally equal to the sum of the product coefficients, assuming everything is a gas, minus the sum of the reactant coefficients. Okay, so this is going to be a common trend through a lot of the rest of Chem 2, is it's products minus reactants anytime you have to do something like this. So let's look at a generic example here. So let's say we had 3 moles of A plus B forms 4 moles of C plus 2 moles of D, and we have some sort of Kc value for it. Okay, but if they're all gases, what we want to know is, what is Kp? Okay, well, we would just use this equation. Kp equals Kc times R, which is a constant, T, which would have to be given. The delta N of gas is the weird bit. So on this side, we have 3 moles of A and 1 mole of B, so that's 4 moles total. Here we have 4 moles of C and 2 moles of D, which is 6. 6 minus 4 is equal to 2. So what this comes out to is that Kp is equal to Kc times RT squared for this particular reaction, which is why I said on the previous example that it depends on the balanced equation. You can't just assume that that this works out that way. So let's try let's try this example without going through all this legwork, just to see that this equation works. Okay. So 2NO plus O2 forms 2NO2. Kc was given 4.67 times 10 to the 13th. We're going to assume this is at 298 Kelvin. That's room temperature. Okay? And we want to know, what is Kp? Well, it should be equal to Kc times RT raised to some sort of coefficient, or some sort of exponent. On this side, we have 2 moles and 1 mole, so that's 3. On this side, we only have one thing, so it's 2. So this should be equal to Kc times RT to the -1. Right? Products minus reactants equals -1. So this should be -1. So, well, we have all these numbers, so let's plug them in. So this is 4.67 times 10 to the 13th times, I'm going to put a bracket here just to keep the math clear, 0.0821 liter atmospheres per mole Kelvin times 298, which is the temperature. That's also in Kelvin, so that cancels, which is just fine. And essentially you could visualize atmospheres as the unit we're shooting for, and moles per liter is what we're canceling out. So everywhere there's a moles per liter, that'll cancel out and you'll be replaced by atmospheres. So the units kind of make sense. And this is raised to the -1. Okay? So if we type all this in, 4.67 e to the 13th times, I'm going to put this all in parentheses, 0.0821 times 298 raised to the -1. Raised to the -1 is the same thing as this the Kc divided by this entire thing, but I'm just typing it as is on the equation. And I got 1.91 times 10 to the 12th. Kp and Kc both have no units. Because it's Kp, we're assuming that it's this equation with everything in terms of atmospheres. You'll notice that unless there is a huge difference in the number of moles, like if you had 17 moles on this side and 1 mole on this side, your Kp and your Kc are going to be similar in magnitude. It's like 10 to the 12th and 10 to the 13th. They're pretty close. There are times where, like, you know, if this was 10 to the 2nd, this might come out to 10 to the -1st. That's not too far away. But if you get like 10 to the 13th, you're not going to get like 10 to the -5th over here. That's too big of a difference. Okay. But not too terrifying, right? As far as stuff that we deal with in this class. Okay. One more concept here for this video, at least. Okay. So for this part, we're going to talk about anytime you have pure solids and pure liquids. So we've talked about things that are aqueous, that's what Kc is. We talked about things that are gases, which is Kp. So what we need to talk about now is equilibria, which I guess I should point out is the plural of equilibrium, involving pure solids and liquids. So in other words, if something in the equation is labeled as a liquid or a solid as opposed to aqueous or a gas. Okay. Typically these things, I guess I could underline the whole thing. Typically these things are heterogeneous mixtures. So you usually have things that are, you know, aqueous, gases, liquids, solids, a random mixture of things. This stuff is actually pretty easy. It's actually going to save us a lot of time and effort in the next couple chapters. We pretty much ignore solids and liquids. In both Kc and Kp. Okay. For example, calcium carbonate is a solid, limestone if I remember correctly. Okay. And it naturally, like, disintegrates over time to calcium oxide, which is also a solid, and carbon dioxide, which is a gas. Okay. If we were going to write Kc for this, we would visualize it as this times this divided by this. But the solids and liquids, we can ignore them, so they just kind of vanish. So Kc for this is literally the concentration of CO2. And since that's a gas, we could also do it in terms of Kp. Kp is the pressure of CO2. Right? Let's look at another example. Suppose we had water as a liquid at equilibrium with water as a gas. Okay. Because water is a liquid, we can ignore it, so the Kc for this is equal to basically the concentration of the only thing that isn't a liquid here. Kp is equal to basically the pressure of the water. It's literally equal to the vapor pressure of water for this particular example. Okay, so honestly, this is just don't forget to do this, but pretty much if you ever see a pure solid or a liquid in your equilibrium, you pretty much, like, it is there to balance things, but it is not ever going to be part of the Kc or Kp. Okay. All right. I don't know if this is enough space, but we'll figure it out. So, if you guys haven't noticed, we've made it through, I don't know, 14 chapters without needing equilibrium, and now all of a sudden we're talking about equilibrium all day, every day. So, why have we been able to ignore it? Like, basically, when don't we need equilibrium constants? Like, when can we choose to just pretend like they don't exist for a little while? Okay. There's like basically 4 situations. I'm just going to list them out here and kind of talk through them. It turns out that if Kc or Kp, because they're always going to be similar in value, is very large. That sounds vague, so I'll give you some specifics. Pretty much anything bigger than 10 to the 15th, you can almost just assume the reaction isn't reversible. Okay, we basically assume the forward reaction is the only reaction that occurs. Okay, assume that it's not reversible. Which makes sense. I mean, there's no reason, if the reaction is only going forward, we don't need to worry about whether there's a reverse reaction. Okay. Similarly, if Kc or Kp is very small. Which would basically be less than 10 to the negative 15th. Okay, so anything from 10 to the negative 15th to 10 to the positive 15th, we kind of need to worry about the equilibrium constant. But this would assume that there's only a reverse reaction and there's no forward reaction, so basically the reaction won't happen. Okay, so yeah, these things, there's a pretty broad range. Anything from 10 to the positive 15th to 10 to the negative 15th is a very broad range where equilibrium constants matter. Anything outside of that, we either assume it's not going to be reversed or it's not going forward. Okay, the third one is a little subtle and it's a little weird. It turns out that although equilibrium constants are related to kinetics, to reaction rates, it turns out that if kinetics plays a dominant role, it might, might override the need for equilibrium constants. So if kinetics plays a dominant role. So in other words, what we mean is it is a very slow reaction. So for example, if we just looked at the equilibrium, I don't actually know the equilibrium constant, we would say that there is an equilibrium where carbon can become graphite or a diamond. Yay! I've mentioned this one a few times in class. Okay, there is an equilibrium, and it's possible that the equilibrium constant is a reasonable value, but the reaction is so slow that we assume that if we had, pencil lead sitting on our desk, that it's not going to turn into diamond before we die. So even though there might be a reasonable equilibrium constant, it's so slow that we can choose to ignore the equilibrium constant because it doesn't actually matter in that situation. Okay, so yeah, for this chapter and the next couple chapters, equilibrium constants are going to come up all the time. But there are times when we can reasonably ignore them. All right, thanks.